Hi everyone, this is a continuation of our previous video, Chain and Multi-Label Algorithms. Today we will look into new guide to advanced predictive analytics via output code classifier, power transformers, and ensemble approaches. Today we will learn a few more different approaches to perform multi-label multi-class prediction tasks like output code classifier, binary, relevance, adapted algorithm, and ensemble approaches, and of course multi-label for deep learning. So let's start with the output code classifier. Output code classifier. Error correcting output code based strategies are fairly different from one versus the rest and one versus one. With these strategies, each class is represented in a Euclidean space where each dimension can only be 0 or 1. Another way to put it is that each class is represented by a binary code, an array of 0 and 1. The matrix, which keeps track of the location code of each class, is the code book. The code size is the dimensionality of the aforementioned space. Intuitively, each class should be represented by a code as unique as possible, and a good code book should be designed to optimize classification accuracy. And this implementation, we simply use a randomly generated code book as advocated in tree, although more elaborate methods can be added in the future. At the fitting time, one binary classifier power bit in the code book is fitted. At prediction, the classifiers are used to project new points in the class space, and the class closest to the points is chosen. An output code classifier, the code underscore size attribute allows the user to control the number of classifiers that will be used. It is a percentage of the total number of classes. A number between 0 and 1 will require fewer classes than 1 versus the rest. In theory, log2 n underscore classes by n underscore classes is sufficient to represent each class ambiguously. However, in practice, it may not lead to good accuracy since log2 n underscore classes is much smaller than the n underscore classes. A number greater than 1 will require more classifiers than 1 versus the rest, and these subclassifiers will, in the theory, correct for the mistakes made by the other classifiers, hence the name error correcting. In practice, however, this may not happen as a classifier mistakes will typically be correlated. The error correcting output codes have a similar effect to bagging. This is for machine learning master. The script in a simple template that we can follow to apply output code classifier. Here it is. We can see from sklearn.multiclass import code output code classifier. Then CLF equals to output code classifier. Then we define the base algorithm. Linear, in here is a linear SVC with the random state equals to 0. And then we fit the data X and Y for the prediction. Next, we have problem transformation. This method can be further carried out in 3 different ways: binary relevance, classifier chains, label power set. Binary relevance, this basically treats each label as a separate single class classification problem. Here is the code snippet from sk multilearn.problem underscore transform import binary relevance, and then again, just like above, classifier equals to binary relevance, and we put the base algorithm in here. It's the Gaussian NP, and after that we fit the data and we continue with our prediction. And the next is classifier chain. We have already seen how it is applied in our previous article. Now, the label power set. Here we transform the problem into multi-class problem with one multi-class classifier is trained on all unique label combinations found in the training data. Label power set gives a unique class to every possible label combination that is present in the training set. In the code, we can see that we are calling from sklearn.multilearn.problem underscore transform import power label power set. Then the label power set with we defined base algorithm, just like in the above, Gaussian NB, and then we fit with train and test data, and we continue with our prediction. Last and not the least is the multi-label classification with deep learning. Deep learning neural networks natively support multi-label classification problems. So here is the sample code that we can use it for multi-label classification problems. And that's it. Here we go. We have our new ways to perform multi-label classification techniques as well. If you enjoyed this article, then I believe you will also enjoy the Part 1 Chain and Multi-Label Algorithms article, which talks about more ways and techniques to perform multi-label, multi-class, and chain classification. Thanks again for your time. If you enjoyed this short article, there are tons of topics in my Advanced Analytics, Data Science, Machine Learning available in my Medium. Take care and enjoy machine learning.